At first glance, nothing seems to move. The ground beneath you feels solid, the horizon unchanged, the oceans contained. But this stillness is an illusion. Beneath every landscape, within every current of air and water, the Earth is being quietly reshaped by forces you cannot see. Entire continents drift without sound. Heat rises through solid rock. Invisible gradients guide the motion of oceans across the planet. These processes do not demand attention, but over time, they transform everything. This is a world defined not by sudden change, but by slow, relentless motion. In this documentary, we will follow these unseen forces, layer by layer, to understand how they shape the Earth across millions of years. If you enjoy deep, calm explorations like this, consider subscribing to Physical Depth and support the journey by liking and sharing this video so more people can experience the hidden dynamics of our planet. From a distance, the Earth appears stable and complete. Its oceans hold their boundaries, continents maintain their shapes, and the atmosphere forms a quiet envelope around the surface. There is no immediate indication of motion or change. Yet beneath this calm appearance, the planet is continuously shaped by forces that cannot be directly seen. These invisible influences operate across every layer of the Earth system. They act within the deep interior, across the surface, and far beyond the atmosphere. Gravity holds the planet together, drawing matter inward and maintaining its overall form. Thermal energy moves slowly through the interior, creating gradual shifts in material over vast periods of time. In the atmosphere, differences in pressure and temperature guide the movement of air, forming patterns that extend across entire hemispheres. None of these processes produce sudden or obvious transformation when observed over short intervals. Instead, they unfold gradually. Rock layers shift by small increments. Air circulates in steady, repeating paths. Ocean waters move in long, continuous currents. Each process is subtle, yet persistent. What makes these forces significant is not their visibility, but their consistency. Over thousands to millions of years, their effects accumulate. Mountains rise to prolonged compression. Ocean basins expand and contract. Climate systems adjust through slow redistributions of energy. The surface of the Earth, though it may appear fixed, is the result of ongoing interaction between these underlying mechanisms. To understand the planet is to recognize that its most influential drivers are not always observable. They do not announce their presence through immediate change. Instead, they operate quietly, shaping the Earth through continuous, measurable influence. In the chapters that follow, these forces will be examined in greater detail, beginning with the most fundamental of them, gravity. The force that defines the structure of the planet itself. Gravity is the most fundamental force shaping the structure of the Earth. It acts continuously on every particle of matter, drawing mass inward toward a common center. Unlike many other forces, gravity does not require contact or visible interaction. Its influence extends through space, quietly organizing the planet from its deepest interior to the outer edges of the atmosphere. In the early stages of planetary formation, gravity played a central role in gathering scattered material. Dust and rock fragments moving through space were gradually pulled together. Over time, these accumulations increased in mass, strengthening their gravitational influence and attracting even more material. This process continued until a coherent planetary body was formed. As mass increased, gravity began to shape the Earth into a sphere. This form arises naturally when matter is pulled equally toward a central point. Irregularities are gradually reduced as material shifts and settles into a balanced configuration. The result is not a perfect sphere, but a slightly flattened shape, influenced by the planet's rotation. Within the Earth, gravity continues to organize materials according to their density. Heavier elements, such as iron and nickel, are drawn deeper toward the core. Lighter materials remain closer to the surface. This internal differentiation creates distinct layers, each with its own physical properties. These layers are not static, but they remain structured under the persistent influence of gravitational force. Gravity also extends beyond the solid Earth. It holds the oceans in place, preventing water from dispersing into space. It anchors the atmosphere, allowing gases to remain close to the surface and form stable pressure systems. Even small variations in gravitational strength across the planet influence how water flows and how air circulates. Although gravity is constant, its effects are not immediately visible in daily observation. It does not produce sudden movement or dramatic change. Instead, it provides a stable framework within which all other planetary processes occur. In this way, gravity can be understood as the underlying condition that makes the Earth's structure possible. Without it, there would be no defined surface, no layered interior, and no atmosphere to sustain long-term environmental systems. Beneath the surface of the Earth, matter is not arranged randomly. Instead, it is organized through a continuous balance between pressure and density. This balance determines how materials are distributed, how they behave under stress, and how the internal structure of the planet remains stable over long periods of time. Pressure increases steadily with depth. Each layer of material supports the weight of everything above it, creating a gradient that extends from the surface to the core. Near the surface, pressure remains relatively low, allowing rocks to maintain rigid forms. Deeper within the Earth, pressure rises to levels that alter the physical properties of materials. Solids become more compact, and in some regions, they begin to flow slowly, despite remaining in a solid state. Density, in contrast, reflects how much mass is contained within a given volume. Materials with higher density tend to move downward under the influence of gravity, while less dense materials remain above them. This process, often referred to as gravitational differentiation, has shaped the internal layering of the Earth since its earliest formation. The interaction between pressure and density creates a state of equilibrium. Dense materials are pulled inward by gravity, but increasing pressure resists further compression. Lighter materials are held above, yet they remain confined by the weight pressing down from above. Over time, this balance leads to a stable arrangement of layers, each defined by its composition and physical behavior. However, this equilibrium is not entirely static. Variations in temperature can alter density, causing material to rise or sink slowly within the mantle. These subtle movements are part of a larger system of internal circulation, driven by differences in heat and maintained by the persistent force of gravity. The result is a planet that appears solid and unmoving at the surface, but internally remains dynamic. Pressure and density do not simply define structure. They regulate motion, control material behavior, and sustain the long-term stability of Earth's interior. Understanding this balance provides a foundation for examining deeper processes, including the gradual movement of material that drives convection within the mantle. Deep beneath the surface, the Earth contains a vast reservoir of energy. This energy does not manifest as rapid motion or visible change, but it persists as heat, slowly moving through the planet's interior. It is this internal energy that sustains many of the long-term processes shaping the Earth over geological time. A significant portion of this heat originates from the planet's formation. In its early state, The Earth accumulated matter through repeated collisions and compression. These processes generated substantial thermal energy, much of which remains stored within the deep interior. Although the planet has been cooling gradually, this residual heat continues to influence internal conditions. Another ongoing source of energy comes from radioactive decay. Certain elements within the Earth, such as uranium, thorium, and potassium, undergo slow transformations at the atomic level. These processes release heat continuously, providing a steady internal energy supply. Unlike surface energy sources, this heat is generated from within and remains largely isolated from immediate observation. As heat accumulates in deeper regions, it begins to move outward. This movement does not occur rapidly. Instead, energy is transferred through conduction in some areas and through slow material motion in others. In the mantle, where conditions allow for gradual flow, heat is carried by the movement of solid rock over extended periods. The distribution of internal energy is not uniform. Some regions retain more heat, while others lose it more efficiently. These variations create subtle imbalances that contribute to internal motion. Over time, such differences become the driving force behind larger processes, including mantle convection and tectonic activity. Despite its scale, this internal energy does not produce immediate or dramatic effects at the surface. Its influence is gradual, operating over millions of years. The surface environment remains relatively stable in the short term, even as heat continues to move beneath it. In this way, the Earth's interior can be understood as a slow-moving system of energy transfer. The heat contained within it sustains the processes that reshape the planet, not through sudden change, but through continuous and measured transformation. The Earth does not remain fixed in its internal arrangement. Even though its surface often appears stable, mass is continuously being redistributed throughout the planet. This movement occurs slowly and across multiple scales, guided by gravity, pressure, temperature differences, and the physical properties of materials. Within the mantle, solid rock behaves in a way that differs from everyday expectations. Under high pressure and sustained heat, it can deform and flow over long periods of time. This motion is not rapid or turbulent. Instead, it unfolds gradually, allowing material to shift position without breaking apart. As a result, mass is constantly being relocated from one region to another. At the surface, redistribution is more visible, though still gradual. Wind transports fine particles across continents. Rivers carry sediment from higher elevations toward lower basins. Glaciers move large volumes of material as they advance and retreat. Each of these processes transfers mass, altering the shape of the landscape over extended timescales. Beneath the oceans, similar processes continue. Sediments settle slowly onto the seafloor, forming layers that accumulate over time. In some regions, sections of the oceanic crust move toward zones where they are gradually drawn downward into the Earth's interior. This process contributes to a long-term cycle in which material is both created and reabsorbed. The redistribution of mass also affects the balance of forces acting on the planet. As material shifts, it can influence pressure distributions and, in subtle ways, even alter the Earth's rotational behavior. These changes are typically small, but they reflect the interconnected nature of planetary systems. What defines this process is its continuity. There is no moment when redistribution stops. Instead, it proceeds without interruption, driven by persistent forces that operate beneath and above the surface. Over time, these movements reshape the Earth in ways that are not immediately apparent. Landscapes evolve, internal structures adjust, and the overall configuration of the planet remains in a state of slow transformation. Beneath the Earth's crust, the mantle extends for thousands of kilometers, forming a vast region where heat and material interact in slow, continuous motion. Within this layer, convection currents act as a primary mechanism for transferring internal energy. These currents are not visible from the surface, yet they play a central role in shaping the planet over long periods of time. Convection begins with differences in temperature. In deeper regions of the mantle, heat from the Earth's interior raises the energy of surrounding material. As this material becomes warmer, it expands slightly and decreases in density. Under the influence of gravity, less dense material tends to rise. This upward movement is gradual, occurring over millions of years rather than moments. As material approaches the upper regions of the mantle, it begins to cool. Heat is transferred toward the surface, and the rising material loses energy. As it cools, its density increases, causing it to slow and eventually sink back toward deeper levels. This downward movement completes a cycle, forming a continuous loop of rising and sinking material. These convection currents do not move in simple or uniform patterns. Instead, they form complex, interconnected systems that vary in scale and intensity. Some currents extend across large portions of the mantle, while others remain more localized. Together, they create a dynamic environment in which material is constantly being rearranged. The motion generated by convection exerts force on the overlying crust. Although the movement is slow, it is persistent. Over long timescales, this interaction contributes to the shifting of tectonic plates, the formation of geological features, and the gradual restructuring of the Earth's surface. Despite its significance, mantle convection does not produce immediate or dramatic changes. Its effects accumulate slowly, becoming apparent only when observed across vast stretches of time. The surface may appear stable, but beneath it, these currents continue to circulate, driven by the steady flow of internal heat. In this way, convection within the mantle serves as a quiet engine of planetary change, linking the Earth's internal energy to the processes that shape its outer form. At the surface of the Earth, the effects of deep internal motion become more apparent through the movement of tectonic plates. These large sections of the lithosphere, composed of the crust and the uppermost mantle, form a fragmented outer shell. Though they appear stable over short periods, they are in continuous motion, guided by forces originating far below. Plate tectonics can be understood as the surface expression of processes occurring within the mantle. Convection currents generate slow, persistent forces that act upon the base of these plates. As material rises and sinks beneath them, it creates conditions that cause the plates to shift, separate, or converge. This movement is measured in centimeters per year, making it imperceptible in daily observation, yet significant over geological time. There are several ways in which plates interact. In some regions, they move apart, creating gaps where new material rises from below and solidifies to form new crust. In others, they move toward one another, leading to compression and the gradual deformation of the surface. In still other areas, plates slide past each other horizontally, redistributing stress along their boundaries. The boundaries between plates are zones of continuous adjustment. Stress accumulates as plates resist movement, then is released in small increments or occasional shifts. These adjustments contribute to the formation of various geological features, including mountain ranges, ocean basins, and fault systems. Despite these interactions, the motion of tectonic plates remains steady and ongoing. It does not begin or end abruptly, but continues as part of a long-term cycle. New crust is formed in some regions, while older crust is gradually reabsorbed in others, maintaining a dynamic balance. Plate tectonics provides a framework for understanding how internal forces shape the visible surface of the Earth. It connects deep, unseen processes with the structures that define the planet's geography. In this way, the shifting of tectonic plates represents a direct link between the Earth's interior dynamics and its evolving outer form. At certain boundaries between tectonic plates, the Earth's surface begins a gradual descent back into the interior. This process, known as subduction, occurs where one plate moves beneath another, guided by differences in density and the persistent influence of gravity. It is a slow and continuous mechanism through which the planet recycles its outer layers. Oceanic crust, which is generally denser and thinner than continental crust, is more likely to be drawn downward. As it moves away from mid-ocean ridges, it cools and becomes increasingly dense. When it eventually encounters another plate, this added density allows it to sink beneath the less dense material. The boundary where this occurs forms a subduction zone, often marked by deep ashen trenches at the surface. As the descending plate moves into the mantle, it carries with it sediments, minerals, and trapped water. Increasing pressure and temperature begin to alter these materials. Some components are released and rise back toward the surface, while others continue deeper, gradually integrating into the surrounding mantle. This process contributes to both the transformation of materials and the redistribution of chemical elements within the Earth. Subduction is not a rapid or uniform process. The downward movement occurs over millions of years, with the plate bending and adjusting as it descends. Along the boundary, stress accumulates as the plates interact, leading to periodic adjustments that reflect the ongoing movement. These shifts are part of a broader system of energy release and redistribution. At the same time, subduction plays a role in maintaining balance within the Earth's crust. While new crust is formed elsewhere, older sections are gradually removed through this process. This continuous cycle prevents the unchecked expansion of the planet's surface and contributes to the long-term stability of its structure. Through subduction, the Earth demonstrates a capacity for renewal. Material that once formed the ocean floor is slowly returned to the interior, where it becomes part of deeper processes. Over time, this cycle ensures that the planet remains dynamic, with its surface and interior linked through ongoing transformation. Mountain ranges emerge not from sudden elevation, but from prolonged periods of compression within the Earth's crust. This process begins where tectonic plates move toward one another, gradually reducing the space between them. The forces involved are steady and persistent, acting over millions of years to reshape the surface. As two plates converge, the material at their boundary experiences increasing pressure. Rather than moving freely, sections of the crust begin to resist this motion. Over time, this resistance leads to deformation. Layers of rock are compressed, folded, and thickened, creating structures that extend both upward and downward. The visible rise of mountains is only one part of a larger reorganization occurring beneath the surface. The formation of mountains is closely linked to the properties of the materials involved. Rocks under high pressure do not always fracture immediately. In many cases, they bend and adjust gradually, accommodating stress through slow deformation. This behavior allows large regions of the crust to change shape without breaking apart completely. As compression continues, the crust becomes thicker in these regions. This increased thickness contributes to elevation, as the surface rises in response to the accumulation of material below. At the same time, deeper portions of the crust extend downward, creating a root-like structure that helps stabilize the mountain range. These processes are not uniform across all regions. Variations in temperature, composition, and the angle of plate interaction influence how mountains form and evolve. Some ranges develop through intense folding, while others are shaped by a combination of compression and uplift. Despite their imposing appearance, mountains are not permanent features. Even as they rise, they are subject to erosion from wind, water, and ice. This creates a balance between uplift and removal, where the visible landscape is constantly being adjusted. The formation of mountains through compression illustrates how invisible forces can produce large-scale structures. What appears as a stable and enduring feature is, in reality, the result of continuous pressure acting over extended time. Not all tectonic movement brings land masses together. In some regions, the Earth's crust is gradually pulled apart, forming what are known as rift zones. These areas mark locations where tectonic plates move away from each other, creating space that is slowly filled by material rising from below. The process begins with the application of tensional forces within the lithosphere. These forces stretch the crust, causing it to thin over time. As the crust becomes less stable, fractures begin to form. These fractures are not isolated. They often develop into extended systems of faults that define the structure of the rift zone. As separation continues, sections of the crust may sink relative to surrounding areas, forming elongated valleys. These depressions, often bordered by steep fault lines, reflect the gradual adjustment of the crust to the applied tension. Beneath these regions, the mantle responds to the thinning of the overlying material. Reduced pressure allows deeper material to rise slowly toward the surface. This upward movement introduces heat into the rift zone. In some cases, molten material reaches the surface and solidifies, contributing to the formation of new crust. Over extended periods, continued separation can transform a continental rift into a new ocean basin, where water eventually fills the expanding gap. Rift zones do not develop rapidly. The stretching of continents occurs over millions of years, with gradual changes accumulating over time. The surface may show visible features such as valleys and volcanic activity, but these are expressions of deeper processes that operate continuously and quietly. The pulling apart of continents demonstrates another aspect of the Earth's dynamic behavior. While some regions are shaped by compression and convergence, others are defined by extension and separation. Together, these opposing movements contribute to the ongoing reconfiguration of the planet's surface. In this way, rift zones represent areas of transition where existing structures are slowly redefined and new geological features begin to emerge through the steady influence of invisible forces. Across the Earth's surface, wind moves continuously, often unnoticed in its long-term effects. Though it may appear gentle or irregular in the moment, air in motion acts as a persistent force that gradually reshapes landscapes. Its influence is most visible in regions where vegetation is sparse and loose material is exposed, but its effects extend across a wide range of environments. Wind originates from differences in atmospheric pressure. As air moves from areas of higher pressure to lower pressure, it gains speed and direction. This movement allows wind to interact with the surface, lifting and transporting small particles such as dust and sand. Over time, this process contributes to the redistribution of material across large distances. The ability of wind to move particles depends on both its velocity and the size of the material. Fine grains can be carried in suspension for extended periods, traveling across continents before settling. Larger particles tend to move closer to the ground, shifting through short, repeated motions. Even these small movements, when sustained over long durations, result in significant changes to the landscape. As wind transports material, it also shapes the surfaces it passes over. Exposed rock can be gradually worn down through abrasion as particles carried by the wind make repeated contact. This process smooths surfaces and creates distinctive formations, often characterized by gentle curves and elongated structures aligned with prevailing wind directions. In areas where transported material accumulates, new landforms begin to develop. Sand dunes form through the steady deposition of particles, building structures that shift slowly as wind patterns change. These formations are not fixed. They respond continuously to variations in airflow, adjusting their shape and position over time. Wind-driven processes operate without interruption. While individual gusts may vary in intensity, the overall movement of air persists as part of the Earth's atmospheric system. Its effects are subtle in the short term, but become increasingly apparent when observed over longer timescales. Through this steady action, wind contributes to the ongoing transformation of the planet's surface. It does not act alone, but as part of a broader network of forces that redistribute material and shape the Earth in gradual and continuous ways. Water moves continuously across the Earth's surface, guided by gravity and shaped by the contours of the land. From rainfall to rivers, this movement forms an interconnected system that gradually alters the landscape. Though individual events may appear temporary, the cumulative effect of flowing water is a persistent process of erosion and redistribution. When water reaches the ground, it begins to follow paths of least resistance. Some of it infiltrates the soil, while the remainder flows over the surface. As it moves, it carries with it small particles of sediment. The ability of water to transport material depends on its velocity and volume. Faster-moving water can carry larger particles, while slower flows tend to deposit the material they have been holding. Over time, these processes create channels that guide future flow. Small streams develop into larger river systems, each contributing to a network that drains entire regions. As water continues to move through these channels, it gradually deepens and widens them. Valleys form, shaped by the consistent removal of material from higher elevations and its transport toward lower areas. Erosion by water is not uniform. It varies with climate, terrain, and the composition of the underlying rock. In some regions, soft materials are removed more easily, leading to rapid changes in the landscape. In others, more resistant rock slows the process, resulting in more gradual transformation. Despite these differences, the overall direction of change remains consistent. As water loses energy, it deposits the material it carries. This often occurs in lower-lying areas, where sediments accumulate to form floodplains, deltas, and other depositional features. These areas reflect the balance between erosion upstream and deposition downstream, linking different parts of the landscape through a continuous exchange of material. Water flow is part of a larger cycle that includes evaporation and precipitation. This cycle ensures that the movement of water is sustained over time. Each phase contributes to the ongoing reshaping of the surface, even when individual changes are not immediately noticeable. Through erosion and deposition, water acts as a steady agent of transformation. Its influence is quiet but persistent, gradually modifying the Earth's surface through continuous motion. Across the world's oceans, vast bodies of water move in slow, continuous patterns known as ocean currents. These currents are not immediately visible from the surface, yet they play a central role in distributing heat across the planet. Through their steady motion, they connect distant regions and influence environmental conditions on a global scale. Ocean currents are driven by a combination of forces. Wind acting on the surface initiates movement in the upper layers of the ocean, setting water into motion over large distances. At the same time, differences in temperature and salinity create variations in water density. These differences cause deeper water masses to sink or rise, forming a layered system of circulation that extends from the surface to the ocean floor. Warm water near equatorial regions absorbs a significant amount of solar energy. As currents carry this water toward higher latitudes, heat is gradually released into the surrounding environment. This process moderates temperature differences between regions, reducing extremes and contributing to more balanced climate conditions. In return, cooler water from polar regions flows back toward the equator, maintaining a continuous exchange. The pathways of ocean currents are shaped by the rotation of the Earth and the configuration of continents. Rather than moving in straight lines, currents follow curved routes that form large circular patterns within ocean basins. These patterns remain relatively stable over time, even as their intensity and exact position shift in response to changing conditions. Beneath the surface, deeper currents move more slowly but carry significant volumes of water. These flows are guided primarily by density differences, forming a global system that links all major oceans. Though their movement is gradual, their influence extends across long timescales, contributing to the long-term distribution of heat and dissolved substances. Ocean currents operate continuously, with no clear beginning or end. Their motion reflects a balance between energy input, gravitational forces, and the physical properties of water. While individual variations may occur, the overall system persists as a stable feature of the Earth's environment. Through this steady circulation, the oceans act as a regulating system for planetary temperature. Heat is absorbed, transported, and released in a continuous cycle, supporting the broader balance of the Earth's climate. Along the boundaries between land and ocean, waves move in a continuous rhythm, transferring energy across the water's surface. Though each individual wave appears temporary, their repeated motion exerts a steady influence on coastal environments. Over time, this persistent energy reshapes shorelines, redistributes material, and alters the structure of the land. Waves are generated primarily by wind, acting on the surface of the ocean. As energy is transferred from air to water, it creates oscillating motion that travels across large distances. When these waves approach shallower coastal regions, their behavior changes. The interaction with the seabed slows the lower portion of the wave, causing it to rise and eventually break. This transformation concentrates energy along the shoreline. As waves break, they apply force to the coast. This force can dislodge particles from cliffs, beaches, and seabed surfaces. Material is gradually removed through repeated impact, a process that contributes to coastal erosion. Over extended periods, even solid rock can be worn down, leading to the formation of features such as cliffs, arches, and platforms. At the same time, waves also transport and deposit material. Sediments carried by water are moved along the coast through currents generated by angled wave approach. This movement, often occurring parallel to the shoreline, redistributes sand and other particles, shaping beaches and coastal formations. In some areas, deposition can build up landforms, balancing the effects of erosion elsewhere. The interaction between waves and the coastline is influenced by multiple factors, including wave energy, tidal range, and the composition of coastal materials. Harder rock tends to resist erosion, while softer materials are more easily reshaped. These differences create varied coastal landscapes, each reflecting the balance between removal and accumulation. Wave activity does not cease. It continues day and night, responding to changing wind conditions and seasonal patterns. While individual changes may seem minor, their cumulative effect becomes evident over long periods. Through this ongoing process, coastlines remain in a state of gradual adjustment. Waves do not create sudden transformation, but through persistent action, they redefine the boundary between land and sea. In colder regions of the Earth, ice acts as a powerful yet gradual force of transformation. Unlike flowing water or moving air, ice operates on much longer timescales. Its motion is slow, often imperceptible in the moment, but its cumulative impact on the landscape is substantial. Glaciers form where snowfall accumulates over extended periods and does not fully melt. As layers of snow build up, the weight above compresses the lower layers, transforming them into dense ice. Under this pressure, ice begins to behave less like a rigid solid and more like a material capable of slow movement. Gravity then guides this movement, causing glaciers to flow outward or downhill. This flow is not uniform or rapid. Instead, glaciers advance gradually, sometimes moving only a few centimeters per day. Despite this slow pace, the mass of ice exerts continuous pressure on the ground beneath it. As glaciers move, they interact directly with the surface, picking up rocks and sediment along their path. The material embedded within the ice enhances its ability to reshape the terrain. As glaciers slide, these particles scrape and grind against the underlying rock, a process known as abrasion. Over time, this action smooths surfaces, deepens valleys, and alters the contours of entire regions. In some cases, large sections of rock are loosened and carried away, further contributing to landscape change. Glaciers also transport material over long distances. When the ice eventually melts, it deposits this material in new locations, forming features such as moraines and outwash plains. These deposits reflect the movement of the glacier and mark the extent of its influence. The presence and movement of ice are closely tied to climate conditions. Periods of cooling allow glaciers to expand, while warmer conditions lead to their retreat. These shifts influence not only local landscapes but also broader environmental systems. Ice, as a geological force, operates quietly and persistently. It does not reshape the Earth through sudden events, but through continuous pressure and motion. Over time, its influence becomes evident in the large-scale features it leaves behind, revealing a history of gradual transformation. Within the Earth's atmosphere, air is constantly in motion, guided by differences in pressure that develop across the planet. These pressure systems are not visible, yet they organize the movement of air on both regional and global scales. Through their continuous interaction, they shape weather patterns and contribute to the broader dynamics of the climate system. Atmospheric pressure is determined by the weight of the air above a given location. This weight varies due to changes in temperature and the distribution of air masses. Warm air tends to expand and become less dense, leading to lower pressure at the surface. In contrast, cooler air is denser and contributes to higher pressure. These differences create gradients that drive the movement of air. Air naturally flows from areas of higher pressure to areas of lower pressure. This movement establishes wind patterns that can extend across large distances. While local variations occur, the overall structure of pressure systems tends to follow recognizable patterns, influenced by the distribution of solar energy and the rotation of the Earth. High-pressure systems are generally associated with descending air. As air moves downward, it becomes more stable, often leading to clearer atmospheric conditions. Low-pressure systems, by contrast, involve rising air. As air ascends, it cools and can lead to the formation of clouds and precipitation. These vertical movements are part of a larger cycle that redistributes energy within the atmosphere. The boundaries between different pressure systems are areas of continuous adjustment. Air masses interact along these boundaries, creating zones where changes in weather conditions are more likely to occur. Despite these variations, the underlying process remains steady, driven by persistent differences in pressure. Pressure systems do not remain fixed in one location. They shift gradually, responding to seasonal changes and variations in energy input from the sun. These movements influence the distribution of temperature, moisture, and wind across the planet. Although the effects of atmospheric pressure are often experienced through daily weather, the systems themselves operate continuously in the background. They represent a large-scale organization of air movement, maintained by subtle differences that persist over time. Through this ongoing process, pressure systems help regulate the flow of energy in the atmosphere, contributing to the stability and variability of the Earth's environment. The Earth rotates steadily on its axis, completing one full turn over a consistent period of time. This rotation is not directly perceived in everyday experience, yet it introduces subtle influences that shape the movement of air and water across the planet. One of these influences is known as the Coriolis effect, a result of motion occurring within a rotating system. When air or water begins to move across the Earth's surface, it does not travel in a perfectly straight path. Instead, its trajectory is gradually deflected due to the planet's rotation. This deflection is not caused by an external force acting in a conventional sense, but by the relative motion between the moving object and the rotating surface beneath it. The direction of this deflection depends on location. In the northern hemisphere, moving air and water are gradually redirected toward the right of their path. In the southern hemisphere, the deflection occurs toward the left. This difference arises from the geometry of rotation, as different latitudes move at different velocities relative to the Earth's axis. The magnitude of the Coriolis effect varies with both speed and position. It is minimal near the equator, where rotational influence is more uniform, and becomes more pronounced toward the poles. As a result, large-scale movements, such as atmospheric circulation and ocean currents, are more noticeably shaped by this effect than smaller, localized motions. Over time, the Coriolis effect contributes to the formation of organized patterns. Winds curve into broad circulation systems rather than flowing directly from high-pressure to low-pressure areas. Ocean currents follow curved paths that define large rotating systems within ocean basins. These patterns remain relatively stable, reflecting the continuous influence of planetary rotation. Although the Coriolis effect does not initiate motion, it modifies the direction of movement once it begins. It acts as a guiding influence, shaping the pathways through which air and water travel. This subtle adjustment, applied consistently across the planet, contributes to the overall structure of atmospheric and oceanic systems. In this way, the rotation of the Earth extends its influence beyond simple movement. It introduces a persistent directional effect, quietly organizing large-scale flows and reinforcing the interconnected nature of planetary processes. Across the Earth, temperature is not evenly distributed. Differences in solar heating create gradients that extend from the equator toward the poles, and from the surface into the atmosphere and oceans. These temperature gradients are fundamental to the movement of energy throughout the planet, guiding the flow of air, water, and heat in continuous cycles. At lower latitudes, the Earth receives a higher concentration of solar energy. This input warms the surface and the air above it, creating regions of relatively high temperature. Toward the poles, solar energy arrives at a lower angle and is distributed over a larger area, resulting in colder conditions. And this uneven distribution establishes a persistent gradient between warmer and cooler regions. Energy naturally moves from areas of higher temperature to areas of lower temperature. This transfer does not occur in a single form, but through multiple processes. In the atmosphere, warm air rises and begins to move horizontally, while cooler air moves in to replace it. In the oceans, warmer surface waters gradually shift toward cooler regions, releasing heat along the way. These movements contribute to large-scale circulation systems that redistribute energy across the planet. Without this redistribution, temperature differences would become more extreme. Instead, the continuous flow of energy helps maintain a balance, moderating conditions across different regions. Temperature gradients also exist vertically. The surface absorbs energy from the sun and transfers it upward through the atmosphere. At the same time, heat from the Earth's interior moves outward. These vertical exchanges influence atmospheric stability and the formation of weather patterns. The strength and structure of temperature gradients change over time. Seasonal variations, changes in surface conditions, and shifts in atmospheric composition all influence how energy is absorbed and transferred. Despite these variations, the overall movement of energy remains consistent. Through these gradients, the Earth operates as a system that continuously redistributes heat. Energy flows along predictable paths, guided by differences in temperature and maintained by ongoing solar input. This process supports the stability of environmental systems while allowing for gradual variation. In this way, temperature gradients act as a driving force behind many of the planet's dynamic processes, linking the distribution of energy to the movement of air, water, and matter. Water on Earth moves through a continuous and interconnected system known as the hydrological cycle. This cycle links the oceans, atmosphere, land, and living systems through a series of processes that repeat without a defined beginning or end. Although individual stages may appear separate, they are part of a unified loop driven primarily by solar energy and gravity. The cycle begins with evaporation, where solar heat causes water at the surface, especially from oceans, lakes, and soils, to change from liquid to vapor. This transformation allows water to enter the atmosphere, where it becomes part of the air. Plants also contribute through transpiration, releasing water vapor from their surfaces into the surrounding environment. As water vapor rises, it encounters cooler conditions at higher altitudes. This cooling leads to condensation, where vapor transitions back into liquid form, creating tiny droplets that gather to form clouds. These clouds are not static. They move with atmospheric currents, transporting moisture across regions. When the concentration of water droplets becomes sufficient, precipitation occurs. Water returns to the surface in the form of rain, snow, or other forms, depending on temperature conditions. This process redistributes water across the planet, often far from its original source. Once water reaches the ground, it follows multiple pathways. Some of it flows over the surface, forming streams and rivers that eventually return to the oceans. Another portion infiltrates the soil, replenishing groundwater systems that may remain stored for extended periods before re-emerging. In cold regions, water may become temporarily stored as ice, delaying its return to the cycle. Throughout this process, gravity guides the movement of water across the surface, while solar energy sustains its transformation between states. The balance between these forces ensures that the cycle continues without interruption. The hydrological cycle does not produce immediate large-scale change, but its persistence shapes the environment over time. It influences weather patterns, supports ecosystems, and contributes to the gradual movement of materials across the Earth. In this way, water acts not only as a substance, but as a medium through which energy and matter are continuously exchanged, linking different parts of the planetary system into a stable and ongoing loop. Over extended periods of time, the Earth's climate is not fixed, but remains within a range shaped by a set of regulating mechanisms. These mechanisms do not operate through immediate adjustment. Instead, they function gradually, responding to changes in energy balance, atmospheric composition, and surface conditions. Through their combined influence, they contribute to the long-term stability of the planet's climate system. One of the central aspects of climate regulation is the balance between incoming solar energy and outgoing heat. The Earth continuously absorbs energy from the sun and releases it back into space. When this balance shifts, temperatures adjust over time. Various processes act to moderate these shifts, preventing extreme or rapid divergence under most conditions. The atmosphere plays a key role in this regulation. Certain gases allow solar radiation to pass through, while limiting the escape of heat. This creates a controlled retention of energy, maintaining surface temperatures within a range that supports stable environmental conditions. Changes in the concentration of these gases can alter how efficiently heat is retained or released. Oceans also contribute to long-term climate stability. Due to their large heat capacity, they absorb and store significant amounts of thermal energy. This storage slows the rate of temperature change, allowing the climate system to adjust more gradually. Ocean circulation further redistributes the stored heat, linking distant regions through a continuous exchange. On land, geological processes influence climate over much longer timescales. The weathering of rocks, for example, gradually removes certain gases from the atmosphere, while volcanic activity can reintroduce them. These processes form a slow cycle that affects atmospheric composition and, in turn, temperature regulation. Ice and surface reflectivity also play a role. Bright surfaces, such as ice and snow, reflect a portion of incoming solar radiation back into space. Changes in their extent can influence how much energy is absorbed by the Earth's surface, contributing to feedback mechanisms that either amplify or moderate temperature shifts. These regulatory systems do not act independently. They interact continuously, forming a network of feedback loops that respond to internal and external changes. While fluctuations in climate do occur, the presence of these mechanisms helps maintain a degree of long-term balance. Through this combination of atmospheric, oceanic, and geological processes, the Earth's climate is guided by gradual adjustment rather than abrupt change, reflecting the persistent influence of underlying natural systems. Beneath the surface of the oceans, water moves in slow and continuous patterns that are not immediately visible. Unlike surface currents driven primarily by wind, deep ocean circulation is guided by differences in water density. These differences arise from variations in temperature and salinity, creating a system of movement that extends across great depths. Density increases as water becomes colder or more saline. In polar regions, surface waters lose heat to the atmosphere and often become colder than surrounding waters. At the same time, processes such as the formation of sea ice can increase salinity, as salt is left behind in the remaining liquid water. These combined effects produce water masses that are denser than those in other regions. As density increases, this water begins to sink. The downward movement does not occur rapidly, but it is steady and persistent. Over time, large volumes of dense water descend into the deep ocean, displacing existing water and initiating slow horizontal flows along the ocean floor. In contrast, warmer and less saline water remains closer to the surface. As deep water spreads outward, it gradually mixes with surrounding layers and may eventually rise again in other regions. This process creates a continuous circulation pattern, linking surface and deep ocean systems. The movement of deep ocean water is extremely slow compared to surface currents. It can take centuries for water masses to travel across ocean basins. Despite this slow pace, the scale of the system is vast, and its influence extends across the entire planet. Deep ocean circulation plays an important role in distributing heat, dissolved gases, and nutrients. As water moves through different regions, it carries these elements with it, contributing to the broader balance of oceanic and atmospheric systems. This circulation is maintained by the ongoing formation of dense water in specific regions and its gradual movement through the ocean depths. There is no clear starting point or endpoint, only a continuous loop driven by persistent differences in density. Through this process, The deep ocean becomes an active component of the Earth's system, quietly transporting material and energy over long timescales, guided by the fundamental relationship between temperature, salinity, and density. Across the world's oceans, a slow and continuous system of movement connects distant regions to a process known as thermohaline circulation. This system is driven by differences in temperature and salinity, which together determine the density of seawater. Through these variations, water is set into motion, forming a global pattern of circulation that extends from the surface to the deepest parts of the ocean. Thermohaline circulation can be understood as a large-scale extension of density-driven flow. In certain regions, particularly at high latitudes, surface waters become colder and more saline. As their density increases, they begin to sink, initiating the downward movement that feeds the deeper layers of the ocean. This process establishes the starting points of long, interconnected pathways. Once water descends, it spreads slowly across the ocean floor. These deep currents move at a steady but extremely gradual pace, guided by the contours of the ocean basins. 1,000 times passed. The pace was calm. The bell was flooded with killing light slut. Over long periods, they carry water across vast distances, linking different ocean regions into a single, integrated system. As deep water travels, it gradually mixes with surrounding layers and may eventually rise again, often far from where it originally sank. This upward movement, known as upwelling, returns water to the surface, where it can be warmed and redistributed by surface currents. In this way, the system forms a continuous loop, with no fixed beginning or end. The term global conveyor reflects the scale and connectivity of this process. Water that sinks in one region may take centuries to complete its journey through the system, yet it remains part of a continuous flow that operates without interruption. Along this path, water carries heat, dissolved gases, and nutrients, contributing to the overall balance of oceanic conditions. Thermohaline circulation does not operate in isolation. It interacts with surface currents, atmospheric systems, and the distribution of solar energy. Together, these elements create a complex but stable network of movement that influences climate and ocean structure over long timescales. Through this steady and persistent circulation, the oceans act as a unifying system, linking distant parts of the planet through the gradual movement of water, driven by subtle differences in temperature and salinity. In the depths of the ocean, pressure increases steadily as one moves farther from the surface. This pressure is created by the weight of the water above, forming a gradient that extends from shallow regions to the deepest trenches. Unlike surface conditions, where changes are easily observed, deep ocean pressure operates as a constant and pervasive force that shapes the physical environment. At relatively shallow depths, pressure remains moderate, allowing familiar interactions between water and solid structures. However, as depth increases, the accumulation of overlying water leads to a rapid rise in pressure. In the deepest parts of the ocean, this pressure reaches levels that significantly alter how materials behave. Structures must withstand continuous compression, and even small changes in depth can produce measurable differences. Water itself is only slightly compressible, but under extreme pressure, its properties shift in subtle ways. These changes influence how sound travels, how heat is distributed, and how substances dissolve. Pressure also affects the formation and stability of chemical compounds, contributing to unique conditions found only in deep ocean environments. The seafloor is shaped in part by these pressure conditions. Sediments are compacted more tightly as depth increases, forming dense layers over time. Geological features such as trenches and basins exist within these high-pressure zones, where the weight of the ocean above contributes to their structural stability. Pressure in the deep ocean does not fluctuate rapidly. It remains stable, governed by depth rather than short-term environmental changes. This stability creates a consistent set of conditions that define the deep marine environment. Despite its invisibility, pressure is a fundamental factor influencing how the deep ocean functions. It governs physical interactions, shapes geological formations, and contributes to the overall structure of the ocean system. Through its continuous presence, pressure defines the conditions of the deep ocean, acting as a silent force that maintains order within one of the most remote regions of the planet. Within the ocean, chemical substances are not distributed evenly. Instead, they form gradients, gradual differences in concentration that exist across depth, distance, and environmental conditions. These gradients are shaped by physical processes, such as circulation and pressure, as well as by interactions between water, seafloor materials, and dissolved compounds. Though not visible, they play a significant role in organizing subsea systems. One of the most consistent gradients in the ocean is the variation in dissolved gases. Oxygen, for example, is more abundant near the surface, where it is exchanged with the atmosphere and produced through biological activity. As depth increases, oxygen levels generally decline, influenced by consumption and limited replenishment. At the same time, other substances, such as carbon dioxide and nutrients, may become more concentrated in deeper waters. Temperature and pressure also affect how chemicals behave. Colder water can hold more dissolved gases, while higher pressure alters the way substances interact and remain in solution. These factors combine to create layered chemical environments, each with distinct characteristics that persist over time. At the boundary between the ocean and the seafloor, chemical gradients become more complex. Here, interactions occur between seawater and minerals within the Earth's crust. In some regions, chemical compounds are released from beneath the seafloor, introducing new elements into the surrounding water. These inputs can alter local conditions, creating zones where concentrations differ significantly from the surrounding environment. Diffusion plays an important role in balancing these gradients. Substances naturally move from areas of higher concentration to areas of lower concentration. However, this movement is slow, and gradients can remain stable over long periods, especially in deeper or less dynamic regions. Chemical gradients also influence broader oceanic processes. They contribute to the distribution of nutrients, affect the cycling of elements, and interact with physical circulation patterns. These interactions link chemical behavior to the movement of water and energy throughout the ocean. Through these gradual differences in composition, the ocean maintains a structured chemical environment, while subsea interactions, guided by these gradients, operate continuously, shaping the internal balance of the ocean in subtle but persistent ways. Surrounding the Earth is an invisible field that extends far beyond the surface, forming a protective and organizing influence known as the magnetic field. This field is not static, but continuously generated by processes deep within the planet's interior. Though it cannot be directly observed, its presence can be measured, and its effects can be detected across a wide range of scales. A source of the magnetic field lies within the outer core, where molten iron and other conductive materials move slowly under the influence of heat and rotation. This movement creates electrical currents, and in turn, these currents generate a magnetic field. The process is sustained as long as the internal motion continues, linking the field directly to the dynamic behavior of the Earth's interior. The magnetic field extends outward into space, forming a region known as the magnetosphere. Within this region, charged particles from the Sun are influenced by magnetic forces, altering their paths and reducing their direct interaction with the atmosphere. In this way, The magnetic field acts as a barrier, moderating the impact of solar energy on the Earth's environment. At the surface, the magnetic field is not uniform. Its strength and direction vary depending on location. These variations reflect the complex processes occurring within the core, as well as interactions with external influences. Over long periods, the field itself can change, including gradual shifts in orientation. Despite these variations, the magnetic field remains a stable feature on human timescales. It does not produce visible structures or immediate changes in the landscape, yet it contributes to the overall stability of the planetary system. Its influence extends into navigation, atmospheric interactions, and the behavior of charged particles in near-Earth space. The magnetic field operates continuously, without interruption. It is sustained by internal motion and shaped by external conditions, forming a link between the Earth's interior and its surrounding environment. In this way, the Earth's magnetic field represents another example of an unseen force that shapes the planet, not through direct physical alteration of the surface, but through its persistent influence on the space and energy systems that surround it. Beyond the Earth's surface, gravitational forces continue to act across space, linking the planet to nearby celestial bodies. Among these, the Moon exerts the most consistent and measurable influence. Though distant, its gravitational pull interacts continuously with the Earth, producing effects that extend from the oceans to the planet's internal structure. The most observed rocks and buttes are proud colors. As the Moon's gravity pulls on the Earth, it creates slight distortions in the distribution of ocean water. Water is drawn toward the side of the Earth facing the Moon, forming a gradual rise. At the same time, a corresponding rise occurs on the opposite side, resulting from the combined motion of the Earth and Moon system. These shifts produce the regular pattern of rising and falling sea levels along coastlines. Tidal movement is not limited to the oceans. The solid Earth also experiences subtle deformation under gravitational influence. This effect, though much smaller in scale, reflects the same underlying process, the redistribution of mass in response to external gravitational forces. The interaction between the Earth and the Moon is not static. As the Earth rotates, different regions pass through these areas of gravitational influence, creating a continuous cycle. The timing and magnitude of tides vary depending on the relative positions of the Earth, Moon, and Sun, introducing patterns that repeat over predictable intervals. Over long periods, these gravitational interactions contribute to gradual changes in the Earth's rotational behavior. The transfer of energy within the system leads to small adjustments in rotational speed and the distance between the Earth and the Moon. These changes occur slowly, becoming apparent only across extended timescales. Despite their subtle nature, gravitational interactions with the Moon play a role in shaping environmental conditions. Tidal movement influences coastal systems, ocean circulation, and the distribution of energy within marine environments. Through this continuous exchange, the Earth is not isolated, but part of a larger system of gravitational relationships. The influence of the Moon, though invisible, remains a steady and measurable force, contributing to the ongoing dynamics of the planet. The primary source of energy for the Earth's surface and atmosphere originates from the Sun. This energy arrives in the form of solar radiation, traveling across space and interacting with the planet in continuous and measurable ways. Although the process is constant, its distribution is uneven, shaping many of the large-scale systems that define the Earth's environment. When solar radiation reaches the Earth, a portion is reflected back into space by clouds, atmospheric particles, and bright surface features such as ice. The remaining energy is absorbed by land, oceans, and the atmosphere. This absorbed energy becomes the foundation for temperature differences across the planet, initiating the movement of air and water. The angle at which solar radiation arrives plays a key role in how energy is distributed. Near the equator, sunlight is more direct, concentrating energy over a smaller area and producing higher temperatures. Toward the poles, the same energy is spread over a larger surface, resulting in lower temperatures. This variation establishes a persistent gradient that drives atmospheric and oceanic circulation. Solar energy also varies over time. Daily rotation causes alternating periods of light and darkness, while seasonal changes shift the distribution of energy between hemispheres. These variations influence temperature patterns, weather systems, and biological activity across different regions. As energy is absorbed, it is gradually re-emitted by the Earth in the form of heat. This outgoing energy interacts with the atmosphere, where certain gases influence how efficiently it escapes into space. The balance between incoming solar radiation and outgoing heat determines the overall energy state of the planet. Despite fluctuations, solar radiation provides a continuous input that sustains dynamic processes. It drives the hydrological cycle, influences atmospheric pressure systems, and supports the movement of ocean currents. Without this constant energy source, many of the Earth's active systems would diminish over time. Solar radiation does not act as a force in the mechanical sense, but is an energy input that enables motion and change. Its influence is indirect, yet fundamental. It's shaping conditions that allow other processes to operate. Its complexity. In this way, the Sun serves as a steady driver of planetary activity, supplying the energy that maintains the Earth's interconnected systems and supports their ongoing evolution. No single force operates in isolation on the Earth. Each process, whether driven by gravity, heat, motion, or chemical variation, interacts with others, forming a network of interconnected systems. These interactions occur continuously, linking the interior of the planet to its surface, its oceans, its atmosphere, and the space beyond. Energy entering the Earth system, primarily from solar radiation, is distributed through the atmosphere and oceans. This distribution creates temperature gradients that drive wind patterns and ocean currents. In turn, these movements influence how heat and moisture are transported, shaping weather and long-term climate conditions. At the same time, processes within the Earth's interior contribute to surface change. Heat rising from the mantle drives convection, which influences the movement of tectonic plates. These movements reshape continents and ocean basins, altering the pathways through which atmospheric and oceanic systems operate. The configuration of land and sea, therefore, is not fixed but evolves alongside the forces acting upon it. Water serves as a connecting medium between many of these systems. Through the hydrological cycle, it moves between ocean, atmosphere, and land, carrying energy and material with it. As water flows across the surface, it participates in erosion, reshaping landscapes that were formed by tectonic and geological processes. Chemical interactions further integrate these systems. Substances dissolved in water, exchanged with the atmosphere, or stored within rocks, are continuously cycled through different parts of the planet. These exchanges influence both physical structures and environmental conditions. External influences also contribute to this network. Gravitational interactions affect ocean movement, while the magnetic field shapes how the Earth interacts with solar energy. These forces extend the system beyond the surface, connecting the planet to its surrounding environment. The result is not a collection of separate processes, but a unified system in constant motion. Changes in one area can influence conditions in another, sometimes across great distances and long timescales. Through these interactions, the Earth maintains a dynamic balance. Its systems adjust gradually, responding to internal and external influences while remaining interconnected. In this way, the planet can be understood not as a series of independent parts, but as a continuously interacting whole, shaped by the combined effects of many invisible forces. The Earth does not change rapidly when observed within the span of a human lifetime. Mountains appear fixed, continents seem unmoving, and oceans maintain their boundaries. Yet, across geological time, these features are continuously reshaped through processes that operate at a slow and steady pace. What appears stable in the present is, in reality, part of an ongoing sequence of transformation. Geological time extends far beyond immediate perception. Over millions of years, small and persistent forces accumulate, producing changes that become significant only when viewed across long durations. Tectonic plates shift gradually, carrying continents into new positions. Ocean basins open and close. Mountain ranges rise through compression and are later reduced through erosion. These changes do not occur in isolation. Internal forces, such as mantle convection and heat transfer, interact with surface processes like erosion and sedimentation. As material is uplifted, it is also worn down. As crust is formed, it is eventually recycled back into the Earth's interior. This balance between construction and removal ensures that the planet remains in a state of continuous adjustment. Climate also evolves over geological time. Temperature patterns shift, ice expands and retreats, and sea levels rise and fall. These changes influence the distribution of water, the structure of landscapes, and the movement of materials across the surface. While individual variations may appear gradual, their long-term effects reshape entire regions. The record of these slow processes is preserved in the Earth itself. Layers of rock, patterns in the landscape, and the arrangement of continents all reflect past conditions. By examining these features, it becomes possible to trace the sequence of changes that have occurred over vast periods. What defines geological change is not speed, but persistence. Each process contributes a small effect, repeated continuously over time. The accumulation of these effects produces outcomes that are large in scale, but gradual in development. In this way, the Earth can be understood as a system that evolves through steady progression. Its present form is not permanent, but part of a longer trajectory, shaped by forces that operate beyond immediate observation, revealing their influence only through the passage of time. Throughout the Earth system, forces act continuously, without interruption. They do not rely on sudden events or visible intensity. Instead, they persist through steady influence, shaping the planet in ways that are often too gradual to observe directly. From the deep interior to the outer atmosphere, these forces remain active at all times. Gravity maintains the structure of the Earth, holding its layers in place and guiding the movement of mass. Heat within the interior continues to flow outward, sustaining convection and driving tectonic motion. In the atmosphere and oceans, pressure differences and temperature gradients keep air and water in constant circulation. Each of these processes operates independently, yet they remain connected through the exchange of energy and matter. What defines these forces is their consistency. They do not begin or end abruptly. Instead, they operate as ongoing conditions within the Earth system. Their effects accumulate slowly, becoming visible only when considered across extended periods. Landscapes evolve, climates shift, and internal structures adjust, all as a result of continuous interaction between these underlying mechanisms. The surface of the Earth reflects this persistence. Mountains, valleys, coastlines, and ocean basins are not fixed features, but temporary expressions of deeper processes. Even when change is not immediately apparent, it is still occurring. Movement continues beneath the surface, within the oceans, and throughout the atmosphere. These forces also maintain a form of balance. While some processes build up material, others break it down. While energy enters the system, it is also redistributed and released. This balance does not imply stillness, but rather a dynamic equilibrium in which change is constant yet regulated. Understanding the Earth requires attention not only to what is visible, but to what operates quietly in the background. The most influential processes are often those that act without immediate recognition, shaping the planet through persistence rather than intensity. In this way, the Earth can be seen as a system defined by continuity. Its form is not determined by isolated events, but by the steady presence of forces that act across all scales, guiding the planet through an ongoing process of gradual transformation. What appears stable is only a moment within a much longer process. Beneath every landscape, these invisible forces continue their quiet work, shifting, shaping, and redistributing the planet over time. There is no true stillness, only movement too slow to notice in a single lifetime. Understanding the Earth means recognizing this continuity, not through sudden events, but through persistent change. If this journey helped you see the planet differently, consider subscribing to Physical Depth and share this video so others can explore these quiet forces shaping the world around us.